Welcome back to Lecture 1b, A Brief History of the Universe. Really quickly, if you have any questions or if you find a topic really interesting, feel free to send me a message over Canvas, or you can simply email me and we can discuss what you find fascinating or maybe what you're having trouble comprehending. Our lecture outline for Lecture 1b is broken down into 3 separate parts. The first part will deal with cosmic distances and cosmic timescales, and the second part will discuss origin and evolution of the universe, and then we'll break that down into even smaller scales with the origin and evolution of the solar system. This lesson is just scratching the surface of astronomy. So again, if you find anything fascinating, please let me know and we can discuss further. Before we begin our lecture, there are a couple of terms that we should define that will help us when talking about these really large distances. And so the first is a light year. You might have heard of this one. It is the distance light travels in 1 year, and it roughly equates to about 9 trillion kilometers or about 5 trillion miles. This is necessary because there's a lot of space in space, and when we are talking about distances to even nearby stars, using a kilometer or mile, as you can see, becomes very burdensome. And so a light year is a great way to describe these really large distances. The next one is an astronomical unit, and you might not have heard of this one. That's okay. This one is very important for distances described within our own solar system. And so it is defined as the average distance between the Earth and the Sun. So that's 1 astronomical unit, and it equates to about 150 million kilometers or roughly 93 million miles. So we're still talking about really vast distances even within our own solar system. And so this image is a representation of our universe's history at time 0 to now. And this image shows important transition points in the universe's history, from the cosmic dark ages to the first stars being born, to the death of those stars and black holes and accretion disks. There's a reionization period. We also find where a lot of the modern galaxies were created to now. And so at time 0, a microscopic universe began expanding. We don't know how big the universe is, but it could very well be as big as 7 trillion light years across. And due to the expansion of the universe, it'll be even bigger by the time you are finished listening to me speak about it. If you think the universe as being empty and dark, that's more representative of the current point in the universe's history. If you kind of look here, you kind of see this point is pretty dark. This looks fairly bright, but dark, bright, sort of bright, and then it starts to kind of darken in here. So you can see there is a vast range of time from the first stars to reionization where the universe actually looks bright. So the image that you're seeing here is a representation of the entire sky in every direction if we were to go outside and look, which is all of what has been detected in the universe. And it covers an observable size of about 93 billion light years in diameter. So on the previous slide, we discussed that the universe is probably the size of about 7 trillion light years in diameter, but that's an estimation we don't really know because we actually can't see back in time as far as the Big Bang. Astronomers, cosmologists, theorists, they are all working on ways to be able to do this in the future. But as of right now, the size of the observable universe is about 93 billion light years. So this is what we have been able to observe. And at the center of this image, you can see that you have this line, this light line right here. This is the Milky Way. So the Milky Way is at the very center of this oval, and that's because we are the observers doing the observations, and so we are going to be at the center of our observations. If we were in a galaxy in the Hydra cluster, then the galaxy maybe here would be then here, and everything in the observable universe would have this at the center. And so speaking of the Hydra cluster, you can see other astronomical features like the Hercules supercluster. These clusters are large groupings of galaxies. They almost look like tendrils, or maybe like when you're looking at a sponge and you see this material that's kind of like creating these tendril-like things, and then you have holes in the middle. That's a lot like how our universe looks, and so these large tendrils are groupings of galaxies. And our Milky Way galaxy is also a part of clusters and superclusters. Continuing to move in from 93 billion light years in diameter from the previous slide, we're now going to move into 110 million light years in diameter. And at that stage, we are observing the Virgo supercluster. This supercluster houses many smaller clusters of galaxies, including the local group of galaxies, which you kind of see in the center of the sphere. You can probably guess that this is where the Milky Way is, because it is at the center of what's being observed. There are roughly around 100,000 galaxies within this supercluster, with the highest mass concentrations of galaxies in the Fornax, Eridanus, and the Virgo cluster, which you see are highlighted as yellow. The Virgo cluster alone has roughly 2,000 galaxies. Let's focus on one of the smaller galaxies at the center of the screen, which is that local group. Instead of 110 million light years in diameter, we are now going to zoom in to about roughly 10 million light years in diameter for the local group. This little clustering of galaxies represents the grouping of galaxies for the Triangulum, Andromeda, and the Milky Way. Let's see, here we have the Triangulum, Andromeda, which is a really big galaxy in this local group. I actually think the biggest. And then here is our galaxy, the Milky Way. The smaller bright oval shapes you see around the Milky Way galaxy, right in here, here, even in here, and goodness, even here, and even the Andromeda galaxy, as in here, here, and here, are called satellite galaxies. And these satellite galaxies were possibly from a larger galaxy, maybe more than one, that was cannibalized by the Milky Way and by the Andromeda galaxy. The Milky Way is continuing to eat these smaller galaxies, for example, like the Large Magellanic and the Small Magellanic Cloud satellites, which are visible in the southern hemisphere, not in the north, unfortunately. And this cannibalizing of these smaller galaxies causes the Milky Way and even Andromeda with its satellite galaxies to grow in size. And now we are taking our perspective and moving it inward from a diameter of 10 million light years to 100,000 light years. This is the diameter of just our Milky Way galaxy alone. Because the Milky Way galaxy is a spiral galaxy, you can see the arms that make up the Milky Way. So for example, there is the Scutum Centaurus arm, the Norma arm right in here. So this one is a really large arm that goes all the way out here. The Norma arm seems to do this right in here. We have an outer arm. The Perseus arm is also a very large arm within our Milky Way galaxy. And then if we are to go look in one of the outer arms towards the bottom of the image, you should see a very small dot with the name Sun. This smaller arm moving away from the central region of our galaxy is the home address of our solar system, which is roughly about 27,000 light years away from the galactic center, which is here. Now, the image at the center of your screen is not a real Milky Way image because we've never really been able to photograph it. The reason for that is simply because we are unable to leave the galaxy to then turn around and take this photograph, as you see on your computer screen. The image on the right-hand side shows what the Milky Way would look like if you were able to go out to a very dark sky to observe the summer nighttime sky. The center of the Milky Way galaxy is observable for those living in the northern hemisphere during the summer months. For us here in Arizona, just getting away from the Phoenix area, you have a better shot at seeing a bit more of the galaxy. Also Flagstaff, that's a great place to go to try and view the Milky Way during the summer months. So looking at this image, though it's not apparent that we are looking at the galactic anatomy of a spiral galaxy here in the right-hand side, I mean, looking at that, you would not say, oh yes, we have spiral arms here. It's actually a lot more difficult than that. So figuring out the Milky Way galaxy as a spiral galaxy, like its neighboring galaxies, Triangulum and Andromeda, began probably around the 1780s with William Herschel constructing a map of stars he saw in the night sky. That will carry us to the 1920s with Harlow Shapley proving where the center of the galaxy is located by measuring the distribution of globular clusters. And then Hubble would later prove using Cepheid variable stars, which are these really massive pulsating stars used to find distances to very distant astronomical objects. Hubble would use these Cepheid variable stars to prove that things observed in the night sky were possibly not part of our galaxy, but part of a vast sea of island universes. And so in 1951, with the help of radio astronomy, astronomers were mapping unseen portions and spiral arms of the Milky Way. So proving that the Milky Way galaxy is a spiral galaxy was no small feat, and can't really attribute it to really one person, but to a century, actually centuries of many people. Now let's focus on the red box centering the Orion Spur. You can see almost at the center of this box is the galactic address of our solar system. We have gone from a diameter of roughly 100,000 light years, or the entirety of the Milky Way galaxy, to roughly 3,500 light years, focused on the Orion Spur, which is this here. So this is the Orion Spur. It looks like a very small arm within the Milky Way. This Orion Spur is named after the constellation Orion, which is a very bright winter constellation for the northern hemisphere. And many prominent celestial objects as part of the constellation are found within the Orion Spur, like the two very bright stars of the constellation, Betelgeuse and Rigel, or even the Orion Nebula, which is a stellar nursery. So when you see things that are named after constellation names, that's because when we are looking up at the night sky, we find that these objects kind of lie within the boundaries of that constellation. So it's also, so the Orion spur is called a spur because it was believed to be a minor galactic structure, which we kind of see right in here. I mean, this looks minor, especially compared to maybe Perseus's arm. But some scientists suggest the Orion spur is a branch of the Perseus arm because it is located in the constellation Perseus as seen from Earth. That's why this has that name. Or possibly it's its own independent arm. You can see the sun lies close to the inner rim, about halfway along the arm's length, in a relative cavity in the arm's interstellar medium called the local bubble. So this would be the local bubble. And the star formation rate in Orion's arm, or Orion's spur, is comparable to the galaxy's major spiral arms, like the Perseus arm. So these two, even though this looks more major, they have roughly comparable star formation rates. Now, if we zoom into the part of Orion's arm where we see the sun, we would find not only the sun, but the planets, asteroids, dwarf planets, and comets that make up the solar system. No longer is it beneficial to use light years to describe distances, but instead we use astronomical units. Remember that 1 astronomical unit is the distance from the Earth to the Sun, which is about 150 million kilometers. So within the solar system, we are looking at distances up to at least 50 AU out to the Kuiper Belt region, which is a distance of about 7.5 billion kilometers from the Sun. So this Kuiper Belt region is all the way out here, and this is a very cold region that's made up of many failed planets and comets as well. Within the Kuiper Belt are what's called dwarf planets, and some of these dwarf planets have incredibly long orbits they have to accomplish. One such Kuiper Belt object is Sedna, a dwarf planet with a highly elliptical orbit. At its closest distance from the Sun, just to give you a perspective, it is roughly 76 AU away, so that's at its closest point to the Sun. 76 AU away, which is about 11.4 billion kilometers. And at its farthest distance, because it has a highly elliptical orbit, at its farthest distance, it's about 937 AU away from the Sun. And that would mean that that is 937 Sun to Earth distances in between Sedna and the Sun, which is about 140.2 billion kilometers away, a whole order of magnitude greater. This should show you that even within the solar system, there are vast distances, and measuring distances in kilometers is just not practical. Zooming in even more so, we see Earth with a diameter of roughly 12,756 kilometers. When discussing distance units, we tend to describe distances on Earth in kilometers or miles, and we also use the same metric when discussing traveling to the moon because it is much too close to use astronomical units. For the next part of the lesson, we will move on to the origin and evolution of the universe. Now, this slide will begin a series of slides that look at the history of the universe through the eyes of time, starting at time 0 with the Big Bang. So here we have time 0 to today, covering about a span of 13.8 billion years. This is the whole history of the universe broken down into 7 major epochs. And the 7 epochs are defined as follows. First we have Big Bang, and that is basically starting at time 0. So that is the initial point at for the beginning of the universe. And then the next would be the inflationary event, which you'll see is very short. First particles form after this, about like 1 microsecond. Next are the first nuclei forming from the first particles. We then have the first light, where the first atoms form, the first stars forming, those stars forming whole galaxies in these like dark matter cradles, and then dark energy defined by accelerated expansion, which continues into today with humans observing these phenomena. We'll start with the beginning period of inflation at 0.000 so many 1 seconds after the Big Bang, or 32 places after the decimal point, which makes the resolution of this time pretty incredible. This period allowed for even distribution of energy and the universal laws of physics, because there really wasn't any time available for these things to evolve differently. This inflationary event occurred at such a fast rate, faster than the speed of light even. The volume of the universe increased by a factor of 10 to the 78, which is very hard to imagine. The rate at which the volume increased could be likened to an object that starts out as 1 nanometer across, or about half the width of a DNA molecule, and is then pulled to one approximately 62 trillion miles across, or 10.6 light years. During this very brief period, the universe is too hot and too dense to allow for elements to form. After about 1 microsecond, or 0.00001 seconds after the Big Bang, the conditions of the extremely early universe were just right to allow for subatomic particles to form. These subatomic particles would be neutrinos, quarks, electrons, and protons and neutrons would form from these subatomic particles. Within about 3 minutes after the Big Bang, the universe cooled just enough to allow for these protons and neutrons to form hydrogen nuclei. Because hydrogen is the starting point of nucleosynthesis, which nucleosynthesis is the process by which stars create new atomic nuclei from pre-existing protons and neutrons. This era is also called the era of nucleosynthesis. The hydrogen that is created here is all the hydrogen the universe will probably ever create. Some of the hydrogen nuclei combine to form helium as well, but that should only be a few percent in comparison to how much hydrogen is available. After about 20 minutes since the Big Bang, nucleosynthesis ends and no further nuclei form. This is because electrons couldn't really stay in orbit around the atomic nuclei due to the immense heat and radiation that still flooded the universe at this time. Jumping to roughly 380,000 years after the Big Bang, the universe had expanded and cooled enough for conditions to favor electrons to remain in stable orbits around atomic nuclei. This is when recombination occurred with neutral hydrogen and helium, finally appearing because they could recombine with electrons without easily losing them to stray radiation, like what was happening at 3 minutes past the Big Bang. This is also the time when the cosmic microwave background, or the CMB, as seen on your screen, was generated. The CMB is generated because the atoms that formed entered their lowest energy state quickly after, releasing excess energy in the form of photons that could travel freely through the universe without colliding with anything else along the way. This is the light that makes up the CMB. You can kind of see, you can kind of see here that we do get basically noise coming from every which way of the observable universe. And so the CMB was discovered by chance in 1965 by two radio astronomers, Penzias and Wilson, who registered a radio signal with their telescope that could not be attributed to any precise source in the sky. It seemed to come from everywhere with the same intensity, day or night, winter or summer. They concluded that the signal had to come from outside our galaxy. This discovery is considered to be solid evidence for the Big Bang Theory because the Big Bang Theory predicted that the shock wave of the primordial explosion would still be detectable as kind of like a subtle wallpaper-like thing coming from everywhere behind all galaxy clusters. And we can see that right here. This looks like in radio astronomy, this would be detectable. So a very subtle wallpaper for the universe. Now looking at a universe 100 to 200 million years after the Big Bang, less than 1% of the universe's current age, gas and dust condensed into the very first stars. The first stars were said to probably be massive, possibly even 10,000 times the mass of the Sun, which is roughly 1,000 times bigger than the biggest stars found today. The stars were so massive that they burned through their hydrogen fuel very quickly and collapsed into supernovae less than 1 million years after birth. During these supernova explosions, lighter elements like carbon and phosphorus, and even heavy metals like gold, lead, platinum, silver, and zinc are created and dispersed into the interstellar medium. Later, this debris can be incorporated into new stars, planets, and other bodies that contain these types of heavy elements and lighter elements. Right after the universe began with the Big Bang, everything looked pretty similar in all directions. There were similar amounts of hydrogen, photons, and dark matter everywhere. But small clumps of matter existed, and because of gravity, these clumps continued to grow until becoming big enough to turn gas into stars, and then those stars bunched together to form galaxies at 400 million years after the Big Bang. Right after the Big Bang occurred, there is the first major epoch of an initial expansion. This only lasted a fraction of a second, as we see, until gravity started to slow the universe's inflation down. So this initial expansion is right around here, and it's just, a burst of inflation. And then it begins to slow down. And from here to here, we don't really see this huge increase in expansion. Roughly 9 to 10 billion years after the Big Bang, which is where we are looking now, the universe's expansion started to speed back up, driven by some unknown force. But this unknown force does have a name, and we call it dark energy. We don't really know what it is, but we do see evidence of its existence because the universe is expanding at an accelerating rate. Today, at 13.8 billion years after the Big Bang, we observe that we are still in that accelerating expansion epoch. So our last section of this lecture is timescales of the universe and us. We will talk about the timescales, distances, but really the timescales for the origin of our solar system. Before we get to that, definitely go to Canvas and watch the video, The Cosmic Calendar. All right, so our last section for this lecture is the origin and evolution of the solar system. So star formation happens in places called the interstellar molecular clouds, which are opaque or very dark clumps of very cold gas and dust. Star formation begins when some of these clumps reach a critical mass, which allows them to collapse under their own gravity. The cause for reaching this critical mass could be random fluctuations of density within the cloud, collisions with other parts of the cloud or clouds, or they could also be disturbed by a nearby supernova or star. The disturbance compresses the gas and dust to a point where it has enough gravity to collect more material onto itself. And that more material is coming from the surrounding molecular cloud. And this begins the process of protostar formation. A star-forming region can produce a few to even a few thousand protostars, like you see here in this stellar nursery. So this whole region is one big stellar nursery in a molecular cloud somewhere in our galaxy. There are stars that are very bright and noticeable, while others might still be shrouded in those darker, more opaque regions of the molecular cloud. And some stars will have access to a lot of material as protostars and will therefore form really big, hot stars that burn quickly through their fuel cycle and become a supernova, all within 2 to 3 million years. So if a star ends up building mass very quickly because there's a lot of material available to do so, it's going to leave that protostar phase much quicker and then something that's smaller, and it's going to ramp through its fuel cycle very fast, and that's really not sustainable. The star is constantly fighting gravity. It's constantly fighting to stay in this hydrodynamic state, and so it's not going to want to collapse in on itself if it can help it. And that's really what the fusion of hydrogen into helium, into carbon, so forth and so on, that's what that is. It is giving the star fuel to keep from collapsing in on itself. And so these big stars don't really last that long, and there are supernovae that are triggered within molecular clouds still surrounded by really young, smaller, cooler stars. And so other stars in this stellar nursery, again, may not be as big nor as hot and will therefore begin burning through their fuel cycle much later. And so stars that are smaller and cooler will end up burning through their fuel cycle at a much slower rate, like our sun, and can continue with their nucleosynthesis for not a couple million years, but billions of years. Over time, these stars will use up much of the gas and dust from the original molecular cloud, or they will rid regions of gas and dust with accretionary jets. Some of the material from the molecular cloud, a very small amount compared to the star, will be used to create planets. So if you look at the top right image around here, you'll see what look like rotating spheres of orange rings in each of these images. These images that are captured in infrared are called protoplanetary disks, and they are the beginning stages of planet formation around a protostar. The rings you see have been postulated as protoplanets scooping up disk material as they form. Others have said these represent possible gaps in the system due to a gas giant. As the core of the gas giant takes form, it will open a gap in the protoplanetary disk, creating a pressure maximum that makes it difficult for material from the inner disk to mix with the material from the outer disk. And this is a whole section of research in astrophysics that also will kind of pull in people that might be more chemists or geologists. And we call that branch of science cosmochemistry. And that is the use of meteorites and things that are within the meteorite will tell a story about how these circular protoplanetary disks were created and formed. The solar nebula model postulates that a spinning cloud of dust made of mostly lighter elements, the nebula, conserved angular momentum from the creation of the star and flattened into a protoplanetary disk. This will evolve into a system like our solar system, consisting of a star and orbiting planets. So the first step again for this solar nebula model, here we see it's very opaque. We don't really even see any gaps, and this is mostly material from the molecular cloud that's not exactly being scooped in by the protostar. So we're looking at 1 to 0.1 microns, and even to an extent a few millimeters, though these a few millimeter dust grains can easily be lost to the protostar. Next, we move to from a disk that is fairly opaque to a disk where we're starting to see some rings form. We even might be able to see evidence of a protostar. So we're going from astronomical dust that is microns to millimeters, all the way to planetesimals. And so planetesimals can range from kilometers to hundreds of kilometers, and these really are planet building blocks. So then we move from planetesimals to protoplanets. And these protoplanets can be greater than 1,000 kilometers. And they aren't so rocky looking. They are starting to look more circular. There might even be some planetary differentiation starting to form. And then next, we'll get giant planets accreting, really causing there to be maybe not so easily mixed material from the disk to the outer disks. Now it's starting to kind of segregate some regions within the disk when these giant planets start to form. And this takes about 1 to 10 million years, though we actually might find it's taking a lot less. And the reason I say this is because this is what my advisor and I actually work on. And then the final step are rocky planets, so Earth-like planets that form out of rock and metal, taking about 10 to 100 million years. And these are the final hopeful regions where, I don't know, life can start to form. And so this is just a little schematic that I have seen used time and time again, and it's a good one. It just kind of shows that the early disk, especially for our solar system, was not homogeneous, but what we would call heterogeneous. And so in the middle we would have our protostar still taking on material from the molecular cloud and growing. And then the closer you get to the star, and the closer you also get to this midplane, so it's not just a two-dimensional thing, it's actually three-dimensional. And so most of the material is going to be at the midplane, but there will also be quite a bit of dust so many scale heights away from the midplane. And so the closer you get to the midplane and the closer you get to the star, the hotter it gets, especially very early on when this is very opaque and causing a lot of heating to occur. And so we get a lot of refractory type minerals that will form here first. And as you go further and further out, things tend to not be so gaseous and vapor, but they tend to start maybe forming a bit more solid. This right here is called the frost line, and so the frost line would be more relegated to water. So this represents maybe where water would start to form. Once you get past this, it is very cool, and you'll get a lot of volatile elements and ices forming along with dusty debris. And so it's also hypothesized that it's not just, one frost line for water vapor, but there's multiple frost lines for multiple molecules.